All right, welcome back. Let's get started and take a look at the microstructure that forms in the eutectic system in various compositions. All right, so we're going to go ahead and take a look at that lead-tin phase diagram again, and we're going to take a look at various overall compositions and what it looks like when we cool from the melt. So the first one we're going to look at is a case where we've got very little tin, mostly lead. And so we're way over here at maybe 1 weight percent tin, 99 weight percent lead alloy. So we start way up here in the liquid phase. And so if I was to try to make a sketch of that, it'd be kind of boring, it'd just be liquid. Then as I cool down, I'm going to get a very small range of temperature in which I exist in this alpha plus liquid region. So if I was to hold right in the middle of that range, then I would have this solid and liquid sort of slush picture view here. And if I was to draw a tie line in there, which I know is very small and difficult to do, but if I was, I could do the inverse lever rule, and I would find out what my fractional amount of alpha is in this whole thing here, and my fractional amount that's liquid. So in this case, it doesn't look quite like 50-50. It looks like they've drawn maybe 40% alpha and 60% liquid. All right, so now we're going to keep going, and we go down further, and we pass into the single phase solid solution region, that's alpha. So what happens is that the grains that we grew are started up here, just continue to grow out once we drop into this alpha region, consuming all the liquid. And so we end up with a nice polycrystalline sample. And we've seen a lot of figures like that in the previous chapters. And then that just continues to cool down, and we don't enter the alpha beta region, and so we just stay single phase solid solution alpha. All right, so let's say we repeat that, but now we're a little bit higher in concentration. So now I'm at 15 weight percent tin. So the first three stages look the same. I'm all liquid. I cross into this liquid plus solid region. So I'm starting to get my solid particles growing out of that liquid phase. I cross into the single phase alpha region, and so I get my nice polycrystalline sample with only one phase alpha. But now in this case, I will cross into the alpha plus beta region. So I already have the alpha, and so that just stays the way it is. But what I need to do is get some beta in there. And so once I cross down into this region, what basically is happening is I've exceeded the solubility limit of tin in the lead. And so this tin-rich phase, the beta, has to come out, and it precipitates out just like you would in a precipitation reaction in a liquid solution. And so the beta precipitates out, and you get these little particles of beta. And part of what they're also trying to show you here is that these particles will tend to be fairly small. And they're small because, remember now, the fusion, in order to grow these beta particles, atoms have to diffuse to the particle and attach, and we're in a solid. And solid diffusion is fairly slow. And so these particles do tend to be small. We just get a lot of them, and they're small, right? This is different than up here where we were precipitating out a solid out of a liquid. There, the diffusion is very fast in the liquid, and so we get much bigger particles, and they tend to be more spherical. In the bottom picture in the beta, a lot of times these particles will follow soft directions in the material. They have a preference for the directions they grow in to try and reduce the strain in the lattice, since these beta particles are going to have a different density than the alpha grains themselves. So you can read more about that in your text. So now we come over to a very special point, the eutectic point. And we have something very unique going on, because here we start off with all liquid at the 61.9 weight percent tin alloy. And then when we drop below 183 degrees C, we enter a two-phase region, alpha plus beta. So now I've got alpha and beta forming at the same time, and I have to be able to move tin and lead into these two different phases because they have very different compositions. And so this creates a little bit of a problem. I'm going to just show you what you get first, and then I'll explain it. But what you're going to end up with is a structure that has both alpha and beta. As you can see here, the alpha is kind of shown here as these lighter regions, the pink. The beta is shown in these darker regions, the blue. But you end up with a layered structure. So these are like sheets of alpha and beta very close together and alternating like this. And you'll have different regions that started to form this structure at different orientations, so they come together and form something like a grain boundary. But we get this alternating unique type of structure, and it's referred to as the eutectic structure. So here's a picture of a lead tin eutectic. This is one that's at 61.9 weight% tin, right? And then the remainder is lead. And you can see the layering in this alloy. If you were to etch away one of these phases, the light or the dark, then you could see the fact that these are sheets or layers that are into the material. All right, so what's going on? Why are we forming this layered structure? Well, let's take a look at what the alternative would be first, I guess. Let's say that we have a liquid, and up here I have an alpha particle that's being formed, and over here I have a beta particle that's being formed, just like we would normally with a single phase like alpha coming out of the liquid. Well, since these alpha and beta are very different than the composition of the overall liquid itself, right? So we were looking at a case where the overall composition was, let's see, what were we? Overall it's 61.9. I should have done that. So overall overall the alloy is at 61.9 tin, right? And you can see here, I've labeled, this is from the phase diagram, just looking at the two ends of the tie line. My alpha is sitting at 82 weight% lead. Okay, so it's only 18% tin. And my beta is sitting all the way up at 98% tin. It's only 2 weight% lead. So these are both very different than the overall composition of the liquid at this point. So my alpha wants to get all the lead that it can. So it wants lead to diffuse to the alpha. But in order to do that, I've got to reject the tin that's nearby. So what that means is I'm going to end up creating this region around the particle as it's growing that is very high in tin because I'm consuming all the lead that's there. And now to continue growing, I have to wait for this tin to diffuse away. And that's going to really slow the process down. So I'm going to suck up all the lead, and I'm not going to have enough lead for the continued growth. And the opposite for the beta, I'm going to suck up all the tin, and I'm not going to have enough tin for the continued growth until I get more to diffuse there. And the bigger the particle gets, the bigger this region I have to diffuse through, and the process will shut down and become very, very sluggish. So one of the things I could do then is, why not form a nice thin layered sheet structure? And the advantage of doing that is that when my alpha phase here, that's mostly lead, right? We said that we need to diffuse the tin away from the liquid that's there. Well, now I don't have to diffuse it very far at all because I've got a beta layer that's growing very close. And that beta wants the tin and it wants to get rid of the lead. So it also has this problem where it wants to diffuse that lead out of the way. And that's no problem because now I've got alpha sitting there very close. And so what we do is we're shortening these distances at which we have to move the lead in the tin. Where in my other example, I'd have to move that tin all the way over to wherever that other beta particle is. So this process of making the layers allows for a much faster growth, and it allows my system to solidify quickly. So then this whole front will basically grow out this way as we are parting the compositions in the liquid, moving lead one way and tin the other. So that gives me a layered structure. This layered structure has good mechanical properties. Being layered like this, it means there's lots of phase boundaries that dislocations would have to move through, and each one of these is a different structure, different composition, and so this makes it very difficult, and it really strengthens the alloy. All right, so let's now back off from the eutectic point but move greater than the case where we just had alpha into the alpha beta. And now we're going to look at this case here where we're going to go from all liquid, right, into this alpha plus liquid region where I grow my solid out. And if I look at right on down to the very bottom of this alpha liquid region, at that point I'd have the alpha grown out to whatever my tie line said was my fractional amounts, right? So my tie line, if you imagine a tie line just above this 183 degree line, so it's going to intersect here at alpha, and then on this end it's going to intersect the liquid, right? That's what I have in there, alpha and liquid. And so I could go ahead and do my mass fractions. Remember, opposite sides, so this piece over here is the amount of alpha, and the piece over here is the amount of liquid I have. And they look like they're almost 50-50, not quite. Okay, so let's just call it that. So 50% of my sample at this point is solid. The other 50% is still liquid. Now, in the eutectic case, remember, my liquid, when it goes into this alpha beta region, right, in this layered structure, this is what's forming my eutectic. This is my eutectic reaction. So when I drop below 183 degrees, say this point M here, I still have my alpha that I formed previously. That's not going to change. So that's still there. But everything that was liquid now converts into both alpha and beta in the layered structure. Okay, so it's just the liquid that becomes the eutectic structure. And I'm still left with these spherical particles of alpha that I formed just above 183. All right, so this material then looks sort of interesting now, because now I've got, in this particular case, I have alpha, right, that's in spheres, and I have alpha that's in layers, just to kind of separate out shapes. And then my beta, I only have layers. I didn't form any beta before I got into the alpha beta region. So that's only in layers. So I have different forms, different shapes of my two phases. Now, overall, these alpha, whether it's in the sphere or layer, and the beta have to overall still give me the correct weight fractions as the tie line would tell me. But these are called micro constituents. Okay, it's just referring to the shape, essentially, of the phases that are there. And again, the layered structure is referred to as eutectic. And so we could call the alpha in the layered, let me get another color. So we could call the alpha in the layered structure eutectic alpha. And the beta that's in the layered structure would be a eutectic beta. And now to distinguish the alpha that was formed in spheres, since we have a label for eutectic alpha, eutectic beta, the alpha that's in spheres was formed first upon cooling, and so we refer to it as primary. So a lot of times we will just refer to this as alpha prime, just indicating that it's the alpha that is in the sphere form. It was formed first in the alpha plus liquid region. Okay. Everything relative to cooling. All right, so that's kind of interesting because that means maybe we can do some calculations and figure out now weight fractions of all these separate pieces, just for fun. So here's what it looks like in a real micrograph. So you can clearly see that there are big particles here, spherical particles, and that is my primary alpha, that alpha that was formed in the alpha liquid region, right? So this one was formed in the alpha plus liquid region. Upon cooling, made nice spheres. And then we have the eutectic structure, right, which is just layers. That's all that the eutectic structure means. That's layers of my alpha plus beta. So you can see that in the contrast. Since my alpha here in the primary particles is dark, then the contrast is going to stay the same, and so my dark layers are also alpha. So that's how I can tell which is which in the eutectic structure. So my eutectic alpha is the dark layers, and then the beta then is the lighter layers. So let me just say, don't memorize that alpha is dark and beta is light, because that's not always the case. They can switch contrast. It just depends on how the instrument's set up. What's important is that you identify the primary phase, and whatever color that is, that's the color that same phase would be in the eutectic structure. All right. Now, of course, all of this image would get reversed if we were to come and pick a composition, right, that's over here above the eutectic point, because now I would be going through the beta plus liquid region instead. So I'd end up with primary beta, and then I'd have alpha and beta in my eutectic structure. Okay, so either or. So you either have primary alpha or primary beta, but otherwise the analysis works out to be the same. All right, so next time, I'm going to stop this one here. We're going to go ahead and see if we can calculate the mass fractions of each of those microconstituents in the eutectic system. So alpha primary, alpha eutectic, and beta eutectic, each of those microconstituents.